Now we have some time for non-exact equations made exact. Okay, all right. Sometimes we have some non-exact equations, as you see down here. We checked. We didn't check this one, but it'll turn out to be non-exact. In some cases, we can make them exact by multiplying appropriate integrating factor. And what is the integrating factor? E to the q. Remember? E to the q, where q is an antiderivative. Remember that? Okay, all right. And what's that antiderivative and how do you find it? Here's the key. Let's see. I may want to have a bigger font here. M sub y minus n sub x over n. If this depends on x only, so no y expression, this all cancels out, and only x alone, in that case, you can take the antiderivative by x because no y there, just antiderivative by x, and then get capital Q. And that e to the q is the integrating factor. Now, if you do that, you're going to get something like this. Multiply by that integrating factor, e to the q power, and the right hand side, 0 times something, so it's gone. And then you can combine those two in this expression using using the product rule and chain rule in partial derivative version, basically. Take the partial derivative of m of e to the q power, then, well, derivative of first function, second function, and first function, and then derivative of the second function is what? Derivative by y, and that's going to be constant. That's going to be 0 because this thing does not depend upon y anyway. So this part is gone, and you have m sub y e to qx. And then take this one, this new one, and take the partial derivative by x. And then, again, by product rule and chain rule, we have derivative of the first function, second function, first function, and derivative of the second function. And that's going to be a bit complicated, the same thing. And what's the derivative with respect to x here? By design, you're going to get this because q is antiderivative of that. So we get that. And then if you do some simplification, this n and n cancel out, break up, and cancel, we get the same thing as before. So the conclusion is this equation, this is nu m, this nu n, this is exact. And then you can use previous method. These two are just proofs, so we don't really need these. For the proof we need, but otherwise you don't. Actual computation, you're using this. Nu m, nu n. In the other case, proof is similar. When nx minus my sub m is function of y only, then, well, integrating factor is like this. Let's see. Let's see if we have enough time for that. So m here is x, y. N here is this. And then we checked. This is not exact. So you'll have to do this either this or that. Let's do one of them first. Expand the font a little bit. And then let's do the computation. Okay, the denominator is n. Okay, that goes down to denominator, all right. Now what is m sub y here? This is my function, and take the partial derivative by y. What is it? That's x. Now how about this one? n sub x, we have to take the partial derivative by x. So what do you get? 4x, and then all these are gone. Yeah, I have just 4x. So what do we have? We have negative 3x over, oh wow, denominator is really complicated, so this is certainly not working out. This is not working out. Okay, this didn't work out. Let's do the other one. Let's expand the font. And then denominator is xym, so that goes to denominator. All right, and what's nx? This one, and take the partial derivative by x. What do you get? We get 4x, because these two do not have any x in there. Okay. How about my? Take the partial by y, you're going to get just, oops, x. And let's simplify this. We have 3x over xy, and simplify into 3 over y. Oh yes, this is working out. This is a function of y only, so it fits in the second category here. So let's find out the integrating factor. Q is antiderivative of 3 over y dy, and this is 3 log of y, which is log of y cubed. And let's find the integrating factor. E to the cube power is e to the log of y cubed, so it's y cubed. And if I multiply y cubed to this equation here and there, and times y cubed, that's not going to change anything, then you're going to get an exact equation. So multiply by y cubed. So, and multiply by y cubed. So what is this? Y to the 4th power? Multiply by y cubed. So y cubed, and this is going to be y to the 5th power. Then this is 20y cubed. We got this new equation, and this has to be exact. Do you have time to finish this problem? I don't know. Let me try anyway. So this one by dx. So calculating antiderivative by x only, so I'm going to get 1/2 x squared y to the 4th power, and then I'm going to get function of y alone. Okay, how about the other? Antiderivative of n here. Oops, I need parentheses. And will that lead me to something? 1/4? No, 2/4, so 1/2 x squared y to the 4th power plus 3/6, so 1/2 y to the 6th power minus 24, so 5y to the 4th power plus h of x. And comparing these, are you going to get something? I hope so. Are you getting something? Let's see, this one's common. That one's common. And these are functions of y only. Oh, it is working out. I don't need this part. So looks like I'm going to get f is equal to 1/2 x squared y to the 4th power plus 1/2 y to the 6th power minus 5y to the 4th power, and that is equal to c. And looks like this is the implicit solution that we are looking for. What do we have here? Let me copy and paste it from my answer key over there. And let's check. Are they the same? Oh yes, everything is done correctly. Okay, alright. Here's the full solution. So, we have two possibilities, one or the other. This one didn't turn out okay, alright. This one is function of y only, alright, it checks out. So let's calculate the integrating factor. Antiderivative of this guy. That's capital Q and e to the q power. Okay, that's the integrating factor. Multiply that integrating factor and get new equation. This is exact, so let's go back to the previous method and just follow through. And that's how you get the solution.